All right. So, so far, when we broke off last time, we were talking about how to determine rate coefficients for radical plus stable reactions. And they're the most important kinds of reactions in most combustion systems. And they're really convenient because the one of them is stable, it's easy to know how much of that stable molecule you have. So you can make a mixture up that has a stable, and you know how much it is because you measure it and carefully prepare it. And then you can do the pseudo first order method because the radical will always have concentration way smaller than the stable. So you're always going to naturally be in a pseudo first order situation. And you can use the pseudo first order method. And that has the great advantage you don't need to know the absolute concentration of the radicals. You only have to know a way to measure the relative concentration. Now, in addition to these reactions, which we know how to do, unfortunately, we also need to do some radical plus radical reactions. And they are really difficult because in order to determine the rate coefficient for a radical plus radical reaction, you must know the absolute concentration of at least one of the radicals. And so that's a lot of the work in this field is all about calibrations of how can you prepare an amount of a radical that you know how much it is and get a signal from it, and then you can use that as the calibration signal for whatever actual measurement you have. So you have to prepare, usually typically do a different experiment that makes a known amount of a radical and then use the same detector to measure that and then use that detector in the actual experiment for the reaction. But you can imagine how this could go wrong in so many ways. So this is really hard, and most people don't do it, actually. So if you look up the list of rate coefficients in literature, you'll find way, way huge numbers of these rate coefficients that have been measured, and very few of these have been measured. And then also you need to know products. So often when two species react, particularly if you have big molecules, and one of them, if they have some reactive sites on them, there's typically more than one way that they can react and make more than one product. And for a kinetic model, you need to know the branching of how much of this reaction leads to product A compared to product B. And so that one also means you have to do absolute measurements, absolute calibrations, because you have to measure product A and product B separately and typically with different masses, if they're different in a mass spec, or different spectra, different wavelengths, if you're doing it by spectroscopy. And you need to have absolute calibrations to get the ratio between the two of them. And so that's also kind of painful. But people do it. So let's talk about the radical plus radical here. This is how this one was measured for the reaction of allo radicals with each other. That was one of them I had on the board the other day was C3H5. It's the radical you make from propene, and it's resonantly stabilized because it has a double bond and a radical, then they can flop positions. And so you tend to make a lot of them, and therefore their recombination of the two of them together actually gets to be significant in a lot of systems because the concentration gets pretty high. And so this is how the measurement was done. They have a xenon lamp that shines through the reaction cell, and then it goes into a monochromator, and they can tune to the wavelength and tune to the wavelengths where allo radical absorbs. So that's not so hard. They use an argon fluoride excimer laser to flash this whole, illuminate this whole volume, and they put a precursor in that can break and make allo radical when it breaks. So for example, diallyl. You can put in there if you have a C6 molecule, the right one, it has a weak bond in the middle that can break to make two allo radicals. And so you can flash it as long as you use a wavelength, like argon fluoride wavelength, that corresponds to a double bond absorption. Then you can put enough energy into that molecule to snap the weakest bond, and that will make you your two allos. And then you can measure here, but then you have to do a second experiment to figure out what the absolute absorption strength of the allo radicals are, or alternatively, how to measure exactly how many allo radicals you really made in the cell, so you know the concentration. You need to know it, and you can do absorption spectroscopy. But you have to have some way to get the absolute concentration. If you start with allyl iodide as your precursor, and you assume that when you see an allyl radical, you must have also formed an I atom, because the way you formed it was breaking the Ci bond between the iodine atom and the allyl radical. Then you can measure I atoms. And so you can use a separate wavelength where I atoms absorb. And I atoms, people have studied them a lot. And so the absolute absorption strength of I atoms is known. So you can measure the I atom absorption. And if you assume that the initial amount of allyl formed equals the amount of I atoms formed, then you have a way to figure out what the allyl radicals are. Now, we think about error propagation. Where's the errors coming from? So one is there's an error in that absorption strength of I atoms. So somebody measured it before, but they only have a certain number of significant figures. So there's some error there. And then you have all the noise you have on your actual signal for the allele. Here's another example. This is a HCO radical. This is a very important radical on the way to carbon monoxide. And you can measure it, actually several ways, but one way is you can do it by cavity ring down spectroscopy. The way this one works is that you make the radical inside a cell that's between two high reflectivity mirrors. You send a pulse of light in that's at a wavelength that the radical can absorb, and the pulse goes down. Some of the energy of the light gets absorbed by the HCO radicals in this pass, but most of it does not, because the radical concentration is tiny and the absorption strength is weak. And so then the light bounces back, and some of it gets absorbed again. And then it bounces back again, and some of it gets absorbed again. And it bounces back and forth like 1,000 times. And each time it loses, a parts per million of the light gets absorbed by the molecules, by the radical. And because the radical is there, what you'll see if you watch the amount of light that's leaking through the mirror and coming out is that its intensity drops with time. It would always drop with time, even if there's vacuum, because the mirrors are not perfect. So you lose a little bit of light at each reflection. So that's like the blue curve. When you don't have any radicals, you'll see how fast the light intensity drops with time coming out here. But if you have the radicals present, then you'll see it drops a little bit faster with time, because on each pass, some of the light's being absorbed by the radicals. And so that makes the loss a little bit faster. And what you measure is the time of how long the light signal lasts, or the time constant for how fast it decays. And that turns out to be proportional to the amount of radicals. Okay, so again, you can see this is a little bit indirect. But you can do it. So here's how they did it. They have a photolysis laser that went through the mirror system, but a little bit off axis, illuminated most of the volume, made a bunch of radicals, and then they have the probe laser that's doing its cavity ring down thing, and you're measuring the photons coming through. And that's how you can make it work. In this particular case, the intensity of light coming through was so small that you could see each photon, one photon at a time. So you have to do photon counting optics, electronics, because light is also quantized. We usually don't see it because light's so intense. We get so many photons hitting us at once that we can't tell that it's individual photons. But if you do a very low illumination experiment like this, where you have an extremely good mirror, not much light goes through that mirror because almost all of it's reflected. And so the amount that's coming through is so low that you have to use a detector, a photon counter. But you can tune this wavelength, and you can actually get the actual spectrum of HCO from that. Here's another example. You can use fluorescence to detect things. So for example, the singlet CH2 molecule has a nice fluorescent spectrum in the red. And so you can create this one by photolysis of ketene. It makes the singlet CH2 radical plus CO. And then if you have a hydrogen around, some of the CH2 will react with the hydrogen and make methyl radicals and H atoms instead. And you can do the laser-reduced fluorescence of the CH2 and see it going down as the reaction occurs. And you can also turn a different kind of fluorescence, atomic resonance fluorescence for the H atoms, and you can see that that signal is rising. And you vary the time between the flash and when the flash of the photolysis, when you make the radicals, and the flash of the detection. A different example is you want to, say, react ethyl radicals with O2. In this case, this is a O2 stable, so this is a pseudo first order case. But the problem here is it makes more than one product. So you can make stabilized ethyl peroxyl radical, or you could make ethylene plus HO2. So the same initially formed species from the ethyl radical reacting with O2 can form the peroxyl radical highly excited. That thing can either have collisions that get cooled and get trapped as the peroxyl radical, or it can immediately fall apart to make ethylene plus HO2. And so you want to vary the pressure and the temperature, and that will affect this competition. And it's quite important to know because this kind of peroxyl radical will lead to ignition very fast, whereas this kind of radical typically would lead to quench ignition because the OH bond is very weak and it'll give up its H to cap other radicals very easily. And so it'll tend to suppress the ignition. And a complication is that at high enough temperature, the peroxyl radical might also just have a thermal reaction where it falls apart to the ethylene plus HO2. So you have to also watch out for this. And when people did this, they saw that in addition to these species, they also saw a little bit of OH being formed. And there was a lot of confusion about this, about how you could possibly make OH in this system. And so that was Taj's group was trying to understand that. So here they did two experiments, one with methanol and one with ethane as the species, and then they would switch between them to see how different what was happening with the ethane compared to what happened with methanol. In the methanol system, they think they understood exactly the chemistry, and you can see it looks very simple. Whereas the case with the ethane is doing something funny where it's rising, HO2 signal is rising for a while and then falling later, kind of weird, and rises immediately. So it's like a fast rise, a slow rise, and then a fall. But when you have a lot of reactions like this, you can get multi-exponential decays and most multi-exponential time dependencies. Because if you remember from linear algebra, if you have a system of linear differential equations, you have a bunch of timescales that are all the eigenvalues of the matrix, if you remember that. And so the solutions are actually linear combinations of exponentials of all those eigenvalues. And so if they're all different, you'll get a multi-exponential behavior. For the experimentalists, this is a kind of a challenge because it's hard to have your instrument. For example, here, you can't see the first one very well because it's so fast. And then a lot of times, the timescale separation of some of the eigenvalues are too close together, and it's quite confusing to deconvolute it out of the trace. But you can. If you're lucky, you can kind of actually adjust your conditions to find a case that makes it really clear to get a good separation. All right, so that was all about laser flash photolysis. That's one very popular way to try to make radicals and then determine rate coefficients. Another really popular way, and I know some people in this audience do it, is shock tubes. And that's a way that you can jump the temperature up very fast to initiate the reactions. Shock tubes are a little confusing. See if I can explain for those of you who don't do it. What you have is a tube. It's just a pipe. It's like a closed tube. You have a diaphragm. That's like a piece of aluminum foil, maybe, or a piece of plastic film. And it's separating one region that's a high-pressure region called the driver region, and another region that's at low pressure called the driven region. And what you do is you increase the pressure of this region, or you use a pin and poke a little hole to break the diaphragm. And because there's a pressure difference, if the diaphragm's weak enough, the whole thing will just pop like a balloon, wide open. And you'll suddenly have high-pressure gas touching against low-pressure gas with a very sharp, abrupt drop in pressure. That pressure discontinuity is a shock, and the shock will propagate down the tube. And when the shock passes a region, the shock compresses the gas there very suddenly from low pressure to high pressure. And it's basically an adiabatic compression, so the temperature goes up a lot. Because just like in a piston, if you suddenly slam a piston closed, the gas gets hot. The same thing happens here. So the gas gets hot. And a very weird thing is that when the shock gets to the end, it bounces back, and it keeps heating the gas. And it compresses it again. And so the gas, in what's called the reflected shock, right behind the reflected shock over here, the gas gets really hot because it gets compressed 2 times. The shock wave moves fast. It moves faster than the speed of sound. If you maybe take a shock class to learn about this, it's a little bit weird, but it does. And there's a formula that's called the CJ formula. It tells you how fast the shock will move. And so the shock is moving from where it started right here. It's moving down in position, and the y-axis here is time. So at different times, the shock front is at different positions along until it hits the end, and then it bounces back. Meanwhile, the shock zooms ahead, so it's just a pressure wave. But this gas and this gas are often different. So this gas is typically maybe just helium. And this gas over here is whatever you want to do reactions in. So it might be some helium, but it has a lot of other stuff in it, including all your reactants. And so there's actually a difference between these two gases. Now, because this is high pressure and this is low pressure, you'd expect that eventually, when this reaches equilibrium, that the boundary between these two guys will be somewhere over here, right? Because the high pressure thing will expand and kind of compress the low pressure until they reach pressure equilibrium. That boundary between the compositions is called the contact surface. And that's moving along, but that's moving along at something that's maybe the speed of sound or even slower than the speed of sound. And so that takes longer time to get to the same position. So that's what this line is. When you have the shock like this, you also get like kind of a weird reflected shock thing that goes backwards and bounces off the back wall. And that's what all these things are. And there's like a lot of non-idealities and weird things that are happening that lead to a whole bunch of like additional shocks that will eventually bounce down here, like a rarefaction wave is bouncing this way, and it's going to kind of come back this way eventually. Typically, you don't want to get into that when you're doing a chemistry experiment. All you want is to use the shock, the reflected shock, to suddenly, at this point over here, suddenly jump the temperature up a whole bunch. And then when it goes from room temperature up to something of a couple thousand Kelvin, immediately all kinds of reactions will start because at a couple thousand Kelvin, all the barriers, the EA over RT factor is like way larger, the Boltzmann factors. And so suddenly you have a lot of reactions happen. And that's the purpose of the shock tube. One of the most famous shock tube groups in the world is Ron Hansen's group in Stanford University. And these are some of the pictures of some of the shock tubes that they have there. They typically use laser methods to measure what's happening. So they'll put a laser beam across the shock tube down here, and then they'll measure the absorption. And if you're looking at the color of, say, some radical that can be made by the shock, when the shock wave passes, all of a sudden you'll see that color. Then that light will be absorbed because you've suddenly made a bunch of that radical. And then if you keep monitoring that color, as the radical reacts away, you'll go back to becoming transparent again at that color, and you'll see it go away. So, and you can get the time constant of how fast it goes away, and that's all due to chemical reaction. So you typically make radicals from the thermal dissociation of the precursor. The way that most of the shock tubes work is called single shots. You just break the diaphragm. Once you break it, you can't make it again. So you just get one data point from that one passing of that one shock wave, and that's it. And then if you want to do another experiment, you have to pump out the whole thing. You have to put a new fresh diaphragm in and do it again. It might take you half an hour to start another experiment afterwards. There are some people that have a different thing where it's kind of like a mechanical piston, a magnetic piston thing that jams up and makes the shock. And so that way you can make the shock waves more often because you don't actually break the diaphragm. You just like have a piston motion that forces the shock wave. And so that's an alternative way. This way of breaking the diaphragm is more common and very well characterized. People worked on it for a long time. The other way of trying to run a lot of shocks is kind of more newfangled thing, and people are working out how accurate it really is to do. But it has the advantage that the single shot one is really bad because you can't do the averaging. Yeah. Usually it's different. Usually the high pressure gas on the left usually is like pure inert gas. Usually helium is very common. The one on the right has to have your reactants in it, so it's definitely different. And yeah. At the contact surface where the two of them are touching, there'll be a little bit of mixing, but typically that's moving so slowly that it doesn't get to the region you're looking at for the experiment, which is all the way down at the end, until a long time scale. So when that finally gets close to you, typically you're done your experiment. You hope that all the radicals have reacted away and you're done. But that also means you have like a limited time scale that you can operate with the shock tube before it's all going to be messed up from the contact surface moving, from the reflected rarefaction waves, by a lot of other actually effects happen. So the shock tube measurements are typically like about a millisecond or less. You can get really great data. And when you get out to 10 milliseconds, it's starting a little bit flaky. And when you get longer than 10 milliseconds, you can't believe it at all because it's all perturbed by stuff like the mixing. And there's also some mixing things happen along the walls. It's not a perfectly smooth flow. And there's a lot of details about this, which I don't really know, but that's like a huge issue in the community. And you can try, if you use a bigger diameter shock tube, the walls matter less because you have more of the gases in the center. So Hansen Group does a lot of really big ones. But then, of course, you do a really big one means you have to put a whole lot of precursor in there to get the same concentration. So your budget for buying chemicals can be really high. So anyway, there's a lot of like pros and cons of different ways to do it. And this one is all for, the way I showed it is for measuring immediately during the milliseconds, usually with a laser technique. There are other methods where you look at the final gas that's left. And that's called, for confusingly to me, it's called a single pulse shock tube. But of course, they're both single pulse. But anyway, when they say single pulse shock tube, what they're telling you is they actually have a way to sample the gas instead of trying to measure in real time the changes of the species. They measure the final products. But that also works pretty well. And Jeff Mannion, for example, is a pretty famous practitioner of that kind of method. And that's like looking at the final products, not the rates. All right. So if you do this, here for example, they're trying to measure methyl radical plus OH. So this is a radical-radical reaction. So you're going to need an absolute calibration. I don't remember, but they probably spent 2 years figuring out how to get the absolute calibration for these radicals in their shock tube, figured out some way to do it, and then they can do the measurement. And this reaction has a couple different products and a couple side reactions. And so the analysis gets kind of complicated. So you see the trace of, say, OH or methyl, whatever they're probing. That's what they measured. But then it might be a multi-exponential or not even exponential at all if it's a second-order reaction of radicals. And so you have to fit it. And then it might depend on a couple rate coefficients. And so like in this case, they figured out that it's sensitive to the rate coefficients of these 4 reactions. And it's most sensitive to the one that they wanted to measure, but it also has some sensitivity to the others. And very commonly, like early times, you're most sensitive to the one reaction and not the other. So you might try to make all your data measurements very quick before side reactions can happen significantly. But it's a bit of a project to do this. Here's another one. This is a pseudo first order, so it's easier. It's formaldehyde plus OH. And so here they found a particular laser band that matches up to a certain absorption of OH radicals, and then they can measure that changing. One confusion that happens in these experiments is that the shock tube temperature is so high that the spectrum can be altered. So you have things called hot bands. Like you have different energy levels of the OH, for example, might be populated that you would never see at room temperature. So if you take a room temperature spectrum of OH, it will look different than the temperature of the spectrum of OH at 2000 Kelvin. So if you have to do things like absolute calibrations, this is like a pretty much of a headache. You also have pressure broadening effects and Doppler broadening, so the peak shapes look different. So in groups like Vasu's group or Hansen group, people spend a lot of time to figure out they really have to understand the spectroscopy of the species they're going to measure really well, particularly for the cases of radical post-radical where they need to have absolute calibrations. And you really have to, again, it might be a couple of years of some graduate student's life figuring out exactly what these absorption cross-sections are. Yeah, all right. And we mentioned before sensitivity analysis and uncertainty analysis. Maybe just this is a nice example of it, where they're trying to determine a rate coefficient for reactions. This is for OH plus methyl. And they have like multiple sources of uncertainty that might confuse their interpretation of the experiment. So they have the experimental data. That's uncontrovertible. They have the points. But what does it mean? Well, part of the reason you have the data is because you have a certain path length of how long your laser beam is interacting with the radicals. But how precisely do you know that length? So there's some error bar about how well you know the length of interaction of the laser beam with the molecules. You have some uncertainty about what your initial concentration of the precursor radicals are. The precursor is that makes the radicals. So for example, the precursor, some of it might stick to the metal walls of the shot tube. And so then you don't have quite as much precursor in the gas phase as you thought you did. So that's like another possible source of error. You might have, when you do the fit, your data has noise, and you fit it to your thing as best you can, but the fit does not exactly match all the data points. And so you have some residual error there. When you take your wavelengths, your laser, you're trying to sit right on top of the absorption peak, but your laser frequency jitters a little bit, and it's not exactly where you expected it to be. So therefore, the absorption strength is not exactly what you expected. So there's some error there. And the laser beam is not a perfect pure wavelength, but it's like has a width. And the absorptions have a width, and so there's some convolution integral you have to do about that. And you have some parameters in that, and they have errors too, so that contributes to some error. And so on and so on. And each of these, they try to quantify how big could this error be. And then after they add up appropriately all these different uncertainties, then they get the actual error bar that they report. So in this case, they think they're uncertain by either it could be 10% lower than what we said or 6% higher, considering all the possible uncertainties. And so that's like a big part of the work, because when you're doing this kind of experiments, you're trying to report for all time the number of the K number that's going to appear in the tables that everybody else in the community is going to use. And so they really want to know the real error bars on it. And so you have to spend quite a lot of time on the error bars, even more time on the error bars and the calibrations than you do in actually doing the experiment to get the K. And then if you typically want to know it at multiple temperatures, so you have to repeat the experiment where you have different intensity shocks that jump the temperature by different amounts. And you have to figure out what temperatures they are, and then you have to do it over and over, and you get lots of points. And you can see funny things that happen. Sometimes it fits like an Arrhenius plot like you expect, and sometimes you get funny bizarro things, and they have to figure out what happened. Another very popular way to do kinetics is flow tubes. So you just have a pipe, you squirt in the two reactants separately, you try to make it so that they mix very rapidly right at the squirt in point, and then there's a carrier gas that's just flowing down the pipe, and it's just carrying the mixture down, and you'll start seeing product forming farther down the pipe. And you just put detectors down there and see. This is one where they used O atoms. Let's see, where are they making them here? Here we go. So I think this is, I'm not really sure. Yeah, I think that they're flowing in water, and they have a plasma thing that's going to make some of the water break up into O atoms. And so they flow it, and then they mix with the other stuff, and then they pump it all out at the end. So they're flowing it down. And in this case, they're also doing pulse photolysis at the same time. So they have like a laser down the path, and they're photolysing some other stuff to make some OH, and they're trying to make O react with OH. So this is pretty tricky, right? You're making two really reactive species, and you're trying to make them react with each other. So you have to know at least the absolute concentration of at least one of them in order to figure out the rate coefficient. And the O atoms here is generated from, wow, this is wild, by N atoms. So the microwave discharge is actually breaking nitrogen gas into N atoms. The N atoms react with NO, makes N2, and that spits out an O atom, and that's the way that the O atoms are formed. And then the water's coming in to get photolysed by the laser so it can make OH. So whoever these guys were, this was back in 1981. They were pretty brave, and they did this complicated experiment. Here's a more recent paper on how to measure what happens in pyrolysis. This is like product measurements. So here you squirt in your gas, in this case it's butanol, and you go through a heater, a furnace, and the gas is cold coming in and suddenly becomes very hot, and it pyrolyzes, and you have the pyrolysis gas in here, and there's a little tiny pinhole through this skimmer and the second skimmer that lets a tiny bit of this gas flow through into the path of a synchrotron. And there the molecules get ionized by the vacuum ultraviolet light from the synchrotron and makes ions, and then they have electrostatic plates that make electric field that push the positive ions up to the mass spec, and they can measure what masses they made. In this way, when you start with butanol and you pyrolyze it, you make a ton of products. It breaks up in tons and tons of different ways, and you can measure them all at once by doing this mass spec thing, because the vacuum ultraviolet will basically ionize all of the hydrocarbons, and so you'll be able to see them all. And so here you can see the butanol going away, and the C4H8 is this butene rising and falling, and benzene forming, and methyl radicals forming, and all kinds of stuff. And you can make quite a lot of measurements this way. And there's a group in China, Fei Qi's group, is really famous for making a lot of measurements like this. You can also do similar things with the synchrotron in the United States in Berkeley. They have a similar setup. And a complication here is that you need to know the temperature. So you have this furnace, you have cold gas coming in, you have like heat transfer from the hot walls of the furnace to the molecules in the flow. And you have to model how many milliseconds were the molecules hot before they got to the pinhole. When they go through the pinhole, they expand into a vacuum, and they get suddenly cooled by the expansion. So you have like this brief moment when they're hot, they react, and then you're trying to intercept the reaction before it's all the way done to capture the intermediate products, things like the methyl radicals. This is actually a very cool kind of experiment for testing a kinetic model, because it measures a lot of species at once, including all the radicals. And so if your model's correct, you'll predict everything right. Model's not always correct. So it's really good at highlighting like which of the species you're mispredicting and exactly what's going on. And you can take the species concentrations, and if you have a complicated model, and actually I think I know this guy who did this. You can try to backfit from that data if you have a kinetic model. But the problem is that typically the fit is not unique. So you can find a fit of parameters of rate coefficients that would match the data, but usually there's more than one possibility of the rate coefficients. And what you find is that you're sensitive to some of the rate coefficients, very sensitive, and those you can determine with great accuracy. But these ones in the middle where the sensitivities are low, they don't affect the results very much, and therefore you really can't infer the rate coefficient very reliably for those reactions. And this is very common. You have a situation that any given experiment is good for determining a couple of parameters, but is really lousy for determining other parameters. And so if you do the sensitivity analyses, then you can see what your experiment is actually good at. It's a good idea to do this before you do the experiment, by the way, because otherwise you may be very frustrated because you're trying to determine this rate coefficient, and then you find out your data is not sensitive to it, and so therefore you can't actually determine it, which would be very disappointing after you blew your 2-week allocation at the synchrotron to do that. When you measure in the synchrotron, one of the things you can do is change the vacuum ultraviolet photon energy, and that has the advantage that each of the different species ionize at slightly different photon energies. And so you can see the different onsets. Like here you're getting some ions, here you're getting something else, here you see another step and getting something else. So you can see that as you change this photon energy, you suddenly get more and more and more signal. And it's because you're actually getting more and more different species to get ionized. And if you can do either measurements or calculations to figure out which species are getting ionized where, it can really help you understand what's going on. And particularly where you have a case where there are multiple isomers. So like these guys all have the same mass, but they're all different isomers. But each isomer has its own ionization potential, so it ionizes at a different wavelength. And so you can deconvolute this photon energy dependence to figure out, or this is like the wavelength of the light, to figure out how much of the stuff was pentenal compared to how much it was cyclopentenol, for example. You can also, an old-fashioned way to do this is to cook stuff and see what you made, right? So this is probably even back from the 19th century. The chemists would just make some stuff out of a pot, they cook it for a while, then you do a lot of analytical chemistry and figure out what the heck it made, and then you infer what the reactions must have been. Because you knew what you put in, you know what you got out. A slightly fancier version of that was done by Baldwin and Walker, where they would have a mixture of hydrogen oxidizing a hydrogen, and they would add a little tiny bit of alkane, and the radicals from the hydrogen oxidation would attack the alkane, and then it would make different products as it attacked the alkane in different spots. And then if you did analytical chemistry afterwards, you could figure it out. They did the same thing with aldehydes, and they also did it for tetramethylbutane. It's like a branchy alkane. And from carefully analyzing what you saw as you changed the concentrations and changed the temperatures and changed the pressure and see what you actually made. Each time you made slightly different mixtures of the products, and then you can infer that the rate coefficients must have been something. And so this is like real chemistry, I guess. So you really have to get in the nitty-gritty of what's actually happening in the mechanism and what can you really infer from what you see from the products. Another way is you want to see something really dramatic, you can try to make an explosion. And hydrogen's really good for this. So with hydrogen, depending on the initial temperature of the mixture and the pressure, when you mix up hydrogen and oxygen, you can either have no explosion or you can have explosions. And there's no doubt here. You don't need some fancy analytical chemist to tell you what happened. Right? If it explodes, you'll know it. And the fact that you get this, where you have called the three limits, the first limit, the second limit, and the third limit, the explosion limits of hydrogen-oxygen mixtures, this is like really telling you this is like super, super nonlinear. Because all you're doing is changing the pressure, and first you make it explode, and then you increase the pressure more and it stops exploding, and then you increase the pressure more and it starts exploding again. That's very weird, right? And so this was observed a long time ago and was kind of a challenge for the community, the combustion community, to figure out what the heck is happening. This is, of course, super important for safety. If you can keep your conditions where you're sure the hydrogen is not going to explode, that's way better than having a condition where it might explode at any time. And so people really wanted to know. And in this case, they figured it out. And the first limit is at very low pressures. What's happening is you actually have radicals going to the wall because they can travel long distances at low pressure. The mean free path is long. And so you actually get very significant loss of radicals at the wall. That makes it not explode. Then when you increase the pressure, you suppress the diffusion because you make the mean free path smaller, and so they can't escape to the wall, and you get an explosion. But then when you increase the pressure further, you start making this three-body reaction of H atoms plus O2 plus whatever the bath gas is, say nitrogen. They together make HO2, and HO2 is the kind of radical that suppresses ignition. So if you go to high enough pressure, you get that happening. But there's a third limit where the H2O2 you form as a product from the HO2, if it has enough collisions, it makes radicals, and you can get explosion again. And so this is just illustrative. This is just for hydrogen and oxygen. If you go with hydrocarbon mixtures, you can get much funkier stuff than this happening. And people have figured out what controls the ignition times for hydrogen and oxygen. There's all these different possible reactions, but there's just a few that matter. Slightly different ones matter at each temperature and each pressure. And this reaction, this is the most important. As I said before, H plus O2 to OH plus O is the main chain branching reaction. So when it amplifies the number of radicals and therefore makes the whole system way more reactive. And so it's usually this works this way, H plus O2. If the temperature is high enough, it'll go to OH plus O. If the temperature is low, the H will just stick to the O2 and you'll make HO2. But if the temperature is high enough, pressure is low enough, you'll make OH plus O, and then the O will attack the fuel, make more OH, and then net you have this reaction happening that you'll make the OH will attack the fuel and make water and a lot of heat because you're oxidizing the fuel. And the radicals will fall apart and make some hydrogen atoms, and they'll go back and do the same thing. And this thing will go over and over again very quickly in microseconds, and you can have an explosion because you make lots and lots of radicals and a lot of heat. And as long as the number of H atoms you make if this X is greater than 1/3, then you get an exponential increase in the number of radicals. So different fuels make different amounts of H's. And the fuels that make a lot of H's explode really a lot. And the ones that don't make so many H's, not so much. All right, we talked about this already. So when you have a premixed flame, you have a lot of chemistry, which I've talked about because that's my favorite topic. But of course, you also have diffusion, right? The flame, why is the flame front moving? Is because heat is moving forward into the unburned mixture. Let's go back and look at the picture. Here's the unburned mixture, here's the burned mixture. The heat is diffusing frontwards, or conducting frontwards into the unburned mixture. And also you have radicals like H atoms that are also diffusing forwards into the unburned mixture. And that diffusion is very important for the rate of the flame speed, how fast the flame is going to propagate. But also the chemistry is really important too because you have to keep making more radicals and making more heat to maintain the diffusive gradient. Otherwise it would go away. So you get a system where you're sensitive both to the transport properties and also to the chemical properties. There's a nice review article about this by Ed Law, our chairman, and finds that basically most of the hydrocarbon fuels have very similar flame speeds because mostly they have heat and H atoms diffusing. That's the same for all of them. And then many hydrocarbons make about the similar number of H atoms per R radical. And so they basically have the same chemistry. And so a lot of fuels are just similar. But there's a couple of weird fuels that can't do one of the steps, and they all have very odd flame speeds. Actually methane is a little bit weird. Acetylene is weird. There's a couple others. Ammonia is really weird. So there's some weird fuels, but many of the hydrocarbons are basically all about the same. And when people do simulations, maybe you guys, some of do this. Do you guys know what Lewis number is? How many know what Lewis number is? Yes. Okay. So very commonly, people start by assuming Lewis number is equal to 1. But it turns out that in a lot of cases, it's not actually equal to 1, and it's different enough from 1 that it actually matters. And so there's some nice papers by Ed Law and by Egafopoulos all about the effects and what that actually does to your real combustion. And as I mentioned, these odd cases, so for example, hydrogen and acetylene. Acetylene is actually weird for an odd reason. It has a strange reactivity of the O atoms. So most of the fuels, the O atoms attack the fuel to make OH, but acetylene reacts much faster with O atoms and it makes some different products. And so that changes the chemistry. Because this reaction is so important, a lot of people tried to measure it. This is state of the art as of 2010, or maybe 2011. And you can see that basically all these groups agree, but they don't agree perfectly, because you can see there's all these points that are off the line. And this turns out to be important because we're so sensitive to the rate coefficient of this reaction. These differences are small enough that you have to worry about how they interpreted their experiments. And so Burke did a nice analysis, theoretically, of what's happening to support that this red line is actually the true rate coefficient. And as with all rate coefficients, you can see it varies a lot, right? So this is a factor of 100 change in the rate coefficient over this temperature range. And this temperature range is not that much. You can also measure the reverse reaction, and that's a way to understand it better. And so you can get O atoms and OH. I showed you that experiment. And it sort of helps you to understand what's going on. It should be consistent with what you got for the H plus O2 in the forward direction. And so this is like a way to check to make sure you really know what you're doing. And again, there's sort of a consensus what the number is, but there's some people who've measured something different, so it's not completely clear. And then the second step is the O atom attacking the fuel, for example, O plus H2. And this was measured really nicely by Sutherland and also Hansen. And I think this is fine. People know what this number is. So this is determined very well. This is quite confusing, that this three-body reaction where the H and the O2 come together, they stick for a little bit, and while they're together, a nitrogen comes in and steals some energy from them and makes them stabilize. We'll show that. So here we have a reaction, H plus O2, and here's HO2. And this is lower, the V of R is lower, the potential energy is lower for HO2. It's more stable than H atoms separately. So it wants to combine, but if you're in a combustion temperature, you're coming in with a Boltzmann population with some extra energy. So you come in with energy like this, and the thing that can happen is you can just go in and bounce off this back wall and come right back out and not have any reaction. And at low pressure, this is what happens. So at low pressure, it doesn't react. So the H atoms bump into the O2s, but they only transiently stick together, and the H atom comes right back off because it has energy way above the dissociation limit. What you need is that while it's in this region, you need to have some collision, say with nitrogen. And the collisions have to lower the energy of the system. And now, once it gets down here, this is now stable, and it'll be HO2. And so this is quite important for the kinetics. And it makes the pressure dependence, because you add more nitrogen, you'll get more HO2. And it looks like a three-body thing, where it's H, O2, and N2 all reacting together. If you try to fit it as a kinetics, you can fit it this way. Really, physically, what's happening is the H is actually sticking to the O2, but it only sticks to it for a very short time. And during that time, it has to suffer a collision to give up the energy to make it work. And this whole thing is called fall off. And this was actually predicted by Lindemann 100 years ago. It's one of the nicest theoretical works with no data. He predicted this would happen. And Joe Michael measured this with flash photolysis. And what they found was that the amount of energy transferred is different for different colliders. So nitrogen takes a certain amount of energy. If you use water vapor, it actually sucks energy out of this complex much better. And people speculate that's because the HO2 can kind of make a hydrogen bond with the water, and that facilitates the energy transfer. So if you do the same thing with water, it's like one collision, you're already stable, because it takes away so much energy. Here's some of the examples with different gases. On the left is rates with different nitrogen, argon, krypton, helium, neon. A lot of these look a lot the same. All these gases look about the same, but then if you do it with water, it's way different. And to try to understand this, people tried to vary the pressure a lot. So Ravi Fernandez did an experiment where he made a super high pressure reactor up to 950 bar to be able to figure out if you can finally reach the high pressure limit where you don't need the collisions are happening all the time and you just make it react the way you might expect from a Boltzmann kind of picture. And so these are data, I think, from Ravi's experiment. Yeah, you can see going up. So as you increase the argon pressure, the effective rate of how much HO2 you're making is going up by orders of magnitude and eventually starts to flatten out when you get up towards 1,000 bar. Yeah, there's 1,000 bar right there. So above 1,000 bar. And people have, there's a way to understand what's happening with the different colliders and make like a dimensionless number that collapses everything to the same plot. And Burke has also looked at this one because it's a very important reaction. So a lot of people worked on this one. You can see here maybe how the rates are different. These are nitrogen and argon as the collider. Here's water vapor. And so it's at least a factor of 10 faster. It makes the effective rate from here to here a factor of 10 faster because the collision is much more effective. And here's the Lindemann's theory for it. What's happening is you have two things react. They make a complex. And then this complex has to suffer a collision to get cooled down. So this is like the energized complex. This is a stable molecule. And when you do if you treat this by the quasi-steady state approximation, you get this formula for the effective K. And it has the concentration of the bath gas in the numerator and the denominator. Then depends on what happens in the denominator. So if the concentration of the bath gas is small, this term is negligible. And then what you have is basically a bunch of constants times the concentration of the bath gas. So that makes it look like a third body reaction, a three-body reaction. If you have a high pressure or a fast stabilization constant, then this term is negligible. And then these KSMs cancel out, and you just get the rate is equal to the forward rate, just as you might expect from before. So that's what Lindemann wrote down. Lindemann wasn't quite right, and Troy did a lot more analysis of it and got a more complicated formula that fixes the Lindemann one a little bit and fits very well. All right, I think that maybe, let's stop now. Yeah, this is, I think maybe enough of this. Let's stop now, and we'll come back at a little bit before 3:15.